Okay, so this now is the data sheet for the actual chip that is connected to the LCD screen. Um, so this is the basically it's a controller slash driver. Now, um, this is actually kind of a fun little story here. I don't know the year of this, but basically this has two modes of operation: 4-bit and 8-bit mode. And the reason it has two different modes of operation, both 4-bit and 8-bit modes, is because literally um, this was back to when they had 4-bit microprocessors and 8-bit microprocessors. That's really what this goes back to, is all the way back to 4 and 8-bit microprocessors. So obviously this LCD screen is old. You'll notice some limitations very quickly on this. The refresh rate on the LCD screen is horrible, in the sense that if you're wanting to do real-time update, you're going to get a big flicker, especially if you're talking in a for loop because of the refresh rate being so slow on it. But for a lot of the purposes we want to kind of use in this course, it's still a great LCD screen because really the purpose isn't necessarily to be using a more expensive LCD screen that has a higher refresh rate, because one, they're more expensive, but two, everything that you're learning here is going to then apply to those um, uh, other LCD screens that are just going to be different number of bits that they run off of, and they're going to have different functionality is all. But the actual kind of powering them up on an I2C and writing an API is going to be the same. Now, the way that this one is going to be operated in is we're going to be operating this in a 4-bit mode. And you might say, well, why? Because we write bytes, and I'll explain in some of the code here on how the reason for this, on why we're putting it in a 4-bit mode as opposed to an 8-bit mode. I honestly don't know if this device, the I2C, would work properly in 8-bit. I've never tried it, but just the way it works in the 4-bit, I'm somewhat skeptical that we would be able to get the 8-bit one working correctly, just with the way that the I2C is connected up to this device. Now, again, here's the data sheet. You can go find it yourself. It's a very big, dense data sheet. There's a lot of information on this. But before you even start going through this, one thing you might want to also notice is that on the back of your board, mine's blue. It's a potentiometer in there with a little, you can get a tiny screwdriver. Sometimes people can even use a pencil or something like that. You want to adjust that because that's the contrast basically. And when you plug it in, the contrast, I mean, by default, you want to turn the contrast up so you can basically see 16 like solid rectangles in line one. At least that's what mine does. So you want to but you don't want to turn it up too high such that you can't see anything else here. So I'm just going to kind of scan through some of this. There's a lot of things like, 5 by 8 dot or 5 by 10. We're 5 by 8. 5 by 10 was a feature when you had one line LCD screens. Some of them were 5 by 8. Now, this is the actual chip as a side note, depending on the pin arrangement. And so you can see, again, this chip is actually, I don't want to say complicated, but look at all of these here. These are controlling all sorts of different segments of the LCD screen. Then really what we're going to be using here are these DB7, 6, 5, and 4 lines. And then we'll also be doing this register, select, read, write, and enable. Because basically the D7, 6, 5, and 4 are going to be our most significant bits, and then the RS, RW, and enable are going to be the least significant bits here when we're doing this. So let's kind of just talk about, let's go back to PSOC before we go through this data sheet, and talk a little bit more about how this device is going to operate here. So instead of handwriting it, I'm going to just put it in comments here because we're going to write an API for it. We're going to just kind of modify this existing code I have. I'm still in debug mode here. So I'm going to put this as comments here. So first off, here, why don't I actually just start block comment here? That would be easier to do. So first off here, we are going to have to split our byte of data for transmission. Because we're putting it in 4-bit mode. So if it's in 4-bit mode, we have to basically transmit the most significant byte and then the least significant byte. Just like when we were reading, it's not a byte. The top 4 bits, the 4 significant bits, and then the least 4 significant bits. Now, as a side note here, half a byte is called a nibble. And that's actually true, so not a bit. Half a byte is called a nibble. And so the way we're going to be transferring these here is that what we're going to have is we're going to create a byte of data from our nibbles. And why are we doing it this way? Well, I'll be honest. You just have to read through the data sheet over and over and over again. The first time I did this for my classes, I'm not joking. I'm not kidding with you guys. I spent probably 5 or 6 hours reading through the data sheet just to make sure I understood how this all works here. And that's just for even just the startup. I'm not even talking about how to do some of the advanced features you can do. I'm just talking about getting the thing started up so that you could print out a message on it, something just even very simple. But the way we're going to do this here is this is the way it is. So remember, we're using these D7, D6, D5, and D4, those from the data sheet here. If I go back to the data sheet for a second and go back to one of these things. Remember, we say we're going to use these. And how do I know? Well, let's go into the 4-bit here. So I just, again, reading it. For 4-bit interface lines, only 4 bus lines DB4 to DB7 are used for transfer. Bus lines DB0 to DB3 are disabled. Okay, so that's good to know. Okay. All right, so then we've got that. And then what's going to have is this is, I would say, sometimes it's, we say NC or DC, don't care or not care, but this is always going to be 0. We're going to make that next one 0. And then what we're going to have is just a second, I forgot again already. All right, so what we're going to have after the 0 is our enable, our read/write, and our register select. To write data to the device, R/W and RS need to be 0. So we need to hold those both at 0. And in fact, if you probe those with power, they're at a 1. They're at logic 1 by default. So to write data to the device, we need to put both of those to 0. We then need to pulse the enable on and off. And if I go to my data sheet again here, we can see how it's going on here. See, this read write is low, pulled low. This register select is pulled low. And this is an instruct and write. So I'm writing an instruction here. I pulse the enable right here. This writes the first nibble. So that's where it's instruction register 7654. Okay? And then I pulse the enable again to write another nibble. Instruction register 3, 2, 1, and 0. And then basically what ends up happening is then, there's a busy flag and address counter read. So this is how you would do a read. And a read, basically, the register select is at a 0, but then we're not writing, so that button is at a 1. And then again, you're still pulsing the enables here. So we'll have to talk about pulsing the enable here. So, but this is a great example figure here. But it took me, as I said, when you read through this stuff, you have to read through it multiple times. I did not get this the first time. I looked at this and I was confused as hell the first time I saw this. I was like, what the heck is going on here? And I mean, someone's like, oh, just use the LCD code that's provided by the user. First off, it's in C++, not in C, which, yeah, you can translate it. But the real purpose is like, well, yeah, I could use someone else's code, but I want to understand how this goes because I want to be able to write APIs. So it took me a while to figure this out, but that's what's going on here. So this is an exact example of what's going to be happening when we are writing our instructions. So now, the instruction register 7654, and then remember, these are on the data lines, but then we're going to have a 0, and we're going to have a 0, and then these are actually going to be, this would be like bit 2, bit 1, and bit 0 is what we're going to have setting that. And so if I go back to it, that's, again, exactly what we have here. D7, D6, D5, D4, 0, the enable, the read write, and the register select. And just going back here again, so what we're going to do is we're going to have to pulse the enable high for a certain period of time and then pull it back low. And then it's going to stay low essentially for as long as we need it to be low. Okay? Now, what we're going to have to do in order to do some of this, there's going to be this new thing that we're going to learn. It's called bit masking. So the bit masking here, let me just kind of show you how we do this here. So let's say we want to write, I'm just going to make up something, 1011 0101 to the LCD. So that's a single byte of data. So that would be some kind of instruction that I'm sending to the device. Well, in order to do that instruction, I have to first divide it up into the 2 nibbles. So I got the 2 nibbles here, okay? And one thing you can do here, and it depends on how you want to write some of this here, but you could look at this byte here. One way to do this here is if I think of this as a byte, so I'm going to think of this as data, okay, is equal to 10110110. That's what data is equal to. So in other words, data is equal to, let's convert that to hex. So that would be 8, 9, 10, 11, which would be B. Let me make sure I converted that. So it'd be 8, 9, 10, 11, so AB, yep, B. And then we have 4 and 1, which is 5. So I have B5 that I want to send. Okay, well first off, I have to strip off the nibbles. So the nibbles here, I can say my high nibble is equal to data ANDed with 0xf0. And why would that work? Why would this line of code here work? High nibble is equal to data ANDed with 0xf0. And what this is going to do here, well, let's think about this. It's a bitwise AND instruction. So I've got 1, 0, 1, 1, 0, 1, 0, 1. That is my data. And then I'm ANDing it with F, which is 1, 1, 1, 1. And then 0, which is 0, 0, 0, 0. Now just remember from basic logic, when you AND anything with 1, this is even just from Boolean algebra, if you AND anything with 1, you just get what you return. And if you think about it here, in other words, I've got 1 ANDed with 1. So that's going to be 1. So my high nibble is equal to 1. Then I have 0 ANDed with 1, which is 0. And then I have 1 ANDed with 1, which of course is 1. 1 ANDed with 1, which is of course 1. And then my zeros ANDed with these zeros, ANDed with this would give me all zeros, because anytime I AND with 0, I get 0. So now I've stripped off my high nibble. Well, how can I do my low nibble? Well, hopefully you guys can see how I would strip off my low nibble. This would be data ANDed with 0x, 0f. And I'm not going to write out here. I encourage you to write out this little bit of line that we did right here. But if I do that, my low nibble is now equal to 0, 0, 0, 0, 0, 1, 0, 1. Now we have to be a little bit careful here because we're trying to, again, transmit this data here. So I'm just getting everything set up for transmission at this point. I'm not transmitting everything. I'm getting things set up for transmission. Now to set up for transmission, we need the nibbles to be in the highest 4 bits. Well, my high nibble is already there. I've got 1, 0, 1, 1. And actually, I've even got my 0 that I need right here and my read, write, and register select already where they need to be. Because remember, going back to the data sheet, that read, write needs to be 0, and that register select needs to be 0 to transmit an instruction, a write. Okay, so I'm already got those. Now I'll have to, this is my enable here. So this is my enable that's going to have to be pulsed. Which we'll talk about how to do that in a second. It's not difficult to do, but we'll talk about how to do that in a second. Maybe probably in the next video. This one's getting a little long here. At least I think it is. Yeah, we're almost at 20 minutes here. So the enable, which needs to be pulsed. Okay, so we'll do that. It's not a big deal. We can figure out how to do that. And that's actually bit 3. So I want to line things up here. But now the low nibble is not set up properly. But this is where we do the bit shifting. So we can say low nibble is equal to low nibble. Bit shifted, make sure you go to the correct direction 4 spots. Now, low nibble is going to be 0, 1, 0, 1, 0, 0, 0, 0. So now we're set up in order. In fact, the thing that's great is we're set up exactly to do my pulses, for my enable pulses in order to write the data to the device. Okay, so we're all ready to go, but let's look at one other thing here. There's one other way we could have done this low nibble one. I could have done low nibble. I could have done it all in one line. Do this in parentheses. 0 data ended with 0x 0f. And then after I do the AND, bit shift it 4 spots to the right. So that basically just cuts out a line of code. It's not necessary to do it that way, but we could do it that way. Now, what we've done here, and we're going to come up with some better names for this instead of 0x0f and 0xf0, we're going to come up with some macros that we're going to use. But what we've just done here is this is called bit masking. And the reason it's called bit masking is it's the idea of that you're putting a mask over your byte of data and you're only letting certain bits get through that mask. You know, so this one here, by doing this AND here, I'm masking. You can think of it however you want to, but I like to think of it as that I'm masking the lower 4 bits. I'm not letting them through. I'm basically putting tape over them or something. And then the other 4 bits are able to get through. So this is really what's called bit masking, and we will be doing a lot of bit masking with the LCD screen here. But we had to first start here just to make sure we start understanding how to read and write. And actually, let's go ahead and just finish off. It's not going to take that long here to do the nibbles here and talk about how we write here. Let's see. I just need to find a timing diagram here for us. It won't take too long. See, this is actually showing how to do some codes. Enable, that's not got the data timing on it here for us. That's not getting the timing. It's a nice diagram, but it's not showing us the times. That's not really timing there. This is just showing 8-bit operation. This is how to actually start the device up. Something. Right here. Enable pulse width. In other words, it has to be 450 nanoseconds high. So it's got to be high for at least 45 nanoseconds, which what we're going to do, because we can't actually delay for that short of period of time, but we can delay for 1 microsecond. It's a minimum. It's not saying, notice how on this it doesn't say anything about typical or max. I mean, you could be silly and do something like, you know, and this is for the read operation and write operation. So it's 450 regardless of whether you're reading or writing. And so it doesn't matter which one you have here as far as the write high or low. You can have the pulse level high being on, as I said, for a second, which is stupid, but you just need to have a minimum of 450 nanoseconds. And because ours really can't delay for 450 nanoseconds, we're going to just delay for a second, 1 microsecond, not a second. That would be stupid. Now I want to show you here something else before I... Here we go. This is what I want to take. So once we do the 1 nanosecond pulse, we're going to have to also then delay additional time for it to actually complete its program. So if we're wanting to turn the display on and off, which we'll talk about all of this stuff later on, we'll get to this. So I'll have a command that I'm going to be writing, but then I need to, once I've pulsed for that 1 microsecond, I need to then delay for another 37 microseconds in order for the command to be executed. And same thing for write data and read data. So to some of the other things. So we're going to have some delays in here. So we're going to have a 1 microsecond delay and then a 37 microsecond delay. So what we're going to do is we're going to actually have some kind of functions within here that aren't really going to be ones that we want the user to have to call. For instance, I don't want the user to have to go through all this detail. I want them to be able to say, you know, turn on the display or turn off the display. I don't want them to have to go through and say like, okay, write a byte of nibble or write a nibble, you know, a high nibble and then write a low nibble. We're going to write all of that code to do that. But I just want to make sure here, going back here, whoops, that's not what I want to go to. Go here, that we start understanding this. So you might want to go through this video again here. This is extremely important that you understand how this works here, because that's what we're going to start with in the next set of videos, is actually writing the functions that will actually write the data to our device. Okay?